Hey, physical science, it's Friday, April 17th right now. We're starting on page 489. 489. Take a look at that picture at the top of 489. You can see a model of a atom. And it's like I have a model of an atom up here. We've got a nucleus, carbon-14 atomic model. And so we've got 6 protons because carbon is element number 6. You can see that right there. Element number 6, 6 protons. And if it weighs 14, then it has 8 neutrons, because that's all the weight of the atom is in the nucleus. The electrons really don't weigh anything. They're just buzzing around like bees around a hive. Then I said that the electron, proton, and neutrons are subatomic particles, that protons and neutrons exist in the nucleus, and that the electrons exist in atomic energy levels called an electron cloud around the nucleus. Now, I'm going to ask you to draw me another atom. We're going to do this one quickly. How about drawing me a carbon atom that weighs 12? Well, first of all, by virtue of being carbon, it's element number 6. By virtue of weighing 12, what's 12 minus 6? There's your nucleus. And if you got 6 positives, you need 6 negatives. How many go on the first energy level? Is 2. And how many go on the next one? Up to 8, but we only have to put 4 of them out. Now there's one more isotope of carbon. What it means is atoms of carbon that have different mass numbers, different weight. And that would be carbon-13. Is it still carbon? Yes. So you have to have 6 protons? Yes. Does it weigh 13? Yes. What's 13 minus 6? 13 minus 6? Is it 7? So we got 6 neutrons. We need a 7th one. And you know what it went to? It went to carbon that weighs 13. Carbon that weighs 12 is in green. Carbon that weighs 13 is the green plus the red dot. Do we still have 6 electrons? If there's 6 positives, do we still have 6 negatives? Now, it's hard to believe that you're going to mess that up, but there'll be some that do. It is so easy to draw an atomic model. Now, what's interesting is that these particles in here, they have taken them into particle accelerators, smashed them, and broken them into bits. And so every proton has 3 quarks inside of it. And every neutron has 3 quarks inside of it. Well, how many quarks are inside of an electron? There are none, because electrons are essentially just energy. So the mass of the atom is in the nucleus. And so you could say that the atom consists of electrons and quarks, and that there are 6 distinct quarks. 3 of them compose a proton, and 3 of them compose a neutron. Up quark, down quark, strange quark, those kinds of things. And how do they find those quarks? It says, page 490. There's a particle accelerator in Batavia, Illinois called the Tevatron. Tevatron, say that. Okay. And it's huge. I mean, it's underground. It's like a great big old culvert, if you please, a big old pipe underground. It's big enough that you can walk around in it, maybe take some vehicles through there. But it goes around in a big old circle underground, maybe 5 miles around. And it's up in Illinois there. And what they do is they speed up particles. They speed up particles. Well, what they might do is they smash these particles, these atoms with nuclear bullets, like protons or neutrons, and they blow them into bits. When they blow them into bits, have you ever seen a jet fly over and you see the cloud behind it? They call that, the icing of the water vapor that's coming out of the exhaust of the aircraft. And so that icing, it's called a concloud or a condensation cloud. It's you can see a cloud behind it. And that's the way it is with quarks. They'll blast the nucleus to bits, and then they will look at the residue in these, it's kind of like an emulsion. We could call it a film that it leaves tracks inside of, kind of like those tracks from the aircraft. And so they're able to find various things. If you look on the bottom of page 490, you'll see that the chambers where you're going to see the inside. Anyway, models, tools for scientists, page 491. I've already talked to you about the atomic model. And here's a guy named John Dalton. Around 1800, he had a theory that matter was composed of extremely small particles called atoms. Take a look at the bullet points right there. That's what I'm going to go down, those bullet points. And Dalton said small particles called atomos. So he was bringing back Democritus's idea 2,000 years earlier. Atoms are indivisible and indestructible. He got that wrong, because now we know that atoms have subatomic parts, protons, neutrons, and electrons, or quarks and electrons. So they are divisible. And atoms of a given element are identical in size, mass, and chemical properties. No, they're not, because of the existence of isotopes. Can you say isotopes? Isotopes are atoms of the same element that have different numbers of neutrons, and therefore it has a different atomic mass in the nucleus. And so you got your carbon 12, you got your carbon 13, you got your carbon 14, and they all differ. Let's make that into carbon 14. You ready? Still carbon, so we got 6 protons, but now instead of 1 extra, we got 2 extra neutrons for a total of 8. 8 plus 6 makes 14. It's a carbon atom that weighs 14 because it's got 14 particles in the nucleus. So he got point 3 wrong also. Atoms of a given element are not identical in size and mass because of the existence of isotopes. Okay, point number 4, atoms of a specific element are different from those of another element. That's true. They differ by 1 proton. If I were to take this atom right here and erase one of the protons, okay? Erase one of the protons. Now we've got 8 neutrons and 5 protons. What's 8 and 5? We have something that weighs 13. What is that something? Now there's only 5 protons. So what is element number 5? Boron. Element number 5 is boron. So this atomic model would represent boron, atom that weighs 13. Now, if you take a look at this, you'll see that boron atoms typically weigh, if you averaged up all the atoms in the universe, they weigh approximately 10.8. So what you have out there are borons that weigh 10, borons that weigh 11. You might even have a heavy boron that weighs 13 that's highly radioactive. I don't know. But this model here is a boron atom because it has 5 protons. That's why it is. And it weighs 13 because it has 13 particles in the nucleus, the way we drew it. Okay, so atoms of a specific element are different from those of another element. Let's go to the next point right down here. Different atoms combine in simple whole number ratios to form compounds. It's H2O1. Those are different whole number ratios. Hydrogen to oxygen is in a ratio of 2 to 1. 2 atoms of hydrogen, 1 atom of oxygen. If you make it a ratio of H to O2 to 2, it isn't water anymore. Does anybody know what that compound is? It is hydrogen peroxide, a different substance. Now, the question is, are these whole numbers, and are they small whole numbers? Are these ratios consisting of small whole numbers? Yeah. What if you had an H 2.5 and an O 3/4? You can't have 3/4 of an oxygen atom. What part are you going to mess up with? You got to have whole numbers. He got that right. Different atoms combine in simple whole number ratios to form compounds. In a chemical reaction, oh, by the way, let me do this. Doesn't exist. In a chemical reaction, atoms are separated, combined, or rearranged. And he got that right too. So you take hydrogen gas and you combine it with oxygen gas, and you're going to get water gas. But as soon as it forms, it's going to form water liquid, because at room temperature, water is a liquid. And so we're talking about hydrogen and oxygen forming that. And what you have to do is this to balance the equation, and you're good to go. We'll talk about balancing equations later. Thank you so much, Mr. Democritus. Thank you so much for Mr. Dalton. Turn the page, 492. Now you've got other visionaries that page 492, 1904, J.J. Thomson without a P, Thomson. J.J. Thomson figured that atoms consisted of spheres. That's what Democritus thought and Dalton thought. But he didn't realize that they were empty spheres. He thought it was solid all the way through. And he thought the electrons on the outside were like raisins on the side of a plum pudding that could be detached. And the way he found that out is that he was able to pass electricity through a gas in a glass tube. And he was able then to shoot this thing called cathode rays. It was a cathode ray tube, CRT. And he was able to shoot from one electrode to another electrode. And so he used electricity. Particles of electricity are called electrons. And so apparently there are materials where the electrons are real loose, like loosey-goosey, and they will, if you put a high voltage on it, it'll knock those electrons loose. And so he used electricity. So since electricity was discovered in 1800, then it wasn't until 1904 that Rutherford determined that the atom had to have loose particles on it, because he knocked them loose from those electrons, and he saw a stream go through this gas. It was kind of a green stream. And I demonstrate that in my classroom, but you have to wait because we're not in there. Rutherford model, 1911, Rutherford said most of the atom is empty space, and that the atom is like the orbit of planets around the sun, with those empty space between the sun and the planets. And the electrons are like the planets, or the other way around. And you can see the picture or the model there that he envisioned. And he felt like the nucleus was positively charged because he shot positive alpha particles from uranium. He gathered from uranium. Those are 2 protons and 2 neutrons. He shot those alpha particles into a gold foil, a foil like this, and the alpha particles went right through the gold foil. Now that looks like they shouldn't be able to, but there's space in there. That's the point he was trying to make. There's spaces between, within the atoms, that the gold alpha particles went right through in the gold foil. And so he proposed the nucleus. He's the nucleus dude. Thomson is the electron dude. And he says the nucleus is positive, and it's in the center of the atom. and the atom is mostly empty space. Now, Niels Bohr put the electrons on energy levels, and that's on page 492. That's the history of the development of the model of the atom. And today's model is on page 493. The illustration is the electron cloud, an area around the nucleus of the atoms where the electrons are most likely to be found. And you can see that picture as well. Kind of like a blur because those electrons are moving so fast. Well, that's it for today. See ya.